Hello, everyone. My name is Gang He. I'm a assistant professor in the Department of Technology and Society. Welcome to EST 603, Energy Systems Analysis. As you can see, I just sent out an announcement that the class will be online or synchronous. We get some feedback and we try to accommodate the need, but unfortunately, it's very hard to get everybody happy. We try, but in the end, still online or synchronous still works best for most of us. So we will keep the format as it was originally designed. If you I know in-person communication is always helpful. So if you feel you want to talk with me, please feel free to use my office hour, or we can make an appointment to make it happen. At the same time, we will use Brightspace for our major class platform. Please pay attention to the announcements, class material updates on Brightspace. That will be our major communication platform. I'll create discussion and you can introduce yourself. You can ask a question there. I may not monitoring the discussion board as much as I wanted, but if I see your question, I will try to respond them. So this is a class for energy system modeling or energy systems analysis. Why we are doing that, I hope to start from a recent example. US passed a historic climate bill, the Inflation Reduction Act, or IRC. As you can see here, Biden signed the historic bill into law. And a question for the policy community or for the lawmakers or for the public is because the bill has a goal to achieve 1 billion tons of carbon emission reduction and to reduce US carbon emission by 40% by 2030 compared to 2005 level. Our question is, can the bill really deliver? How to evaluate the impact? And those questions, we can rely on some models to help us to answer or do some evaluation. For sure, those questions are complicated because it involves how the economic development, how human behavior responds to those incentives. For example, it has incentives, tax rebate for purchase of an EV, purchase of a heat pump, those energy efficiency products. And it's very complicated, as we will discuss later. But system models or energy system analysis can help us to approach those questions. So our homework assignment 0, named it 0 because you don't have to submit it, but please spend some time to explore the homework. I listed 3 mainstream models or by 3 different institutions or research groups, and they come up with their evaluation results. It would be very interesting and very helpful for you to get a sense of how energy system modeling or analysis really work in the real world to assist policy analysis, that this is a great example. So I listed their research, their modeling. One natural questions for you is to give some thought on it, to explore their website and maybe their models, and give a feeling about how they do the analysis, and try to compare their results and think about why there are some disparities and what cause such disparities, and what are the risks and uncertainties in their modeling. Maybe data assumptions, data sources or key assumptions, and try to think about if you were to answer such questions, how would you approach? So those questions will be very helpful if you develop such habit. Think about if you have a real world policy question, and think about how would you use the models, the data you have, and try to give some answer to it. May not be accurate, but it will help us to develop the mindset and the approach, the skill set that needed to approach such question. So why 603 energy systems analysis? So the goal is to develop some quantitative skills or tools so you can use in your research or maybe in your job search, especially if you want to work in think tank or consulting firm or utility companies or energy service companies. Very often they have to address real world policy questions or real world engineering questions that can help them to make decisions. It can be investment decisions, it can be policy decisions, it can be project decisions. And the skill sets that you develop from the class or the observation or might help. And second, we hope using the class to help us to develop the so-called evidence-based energy, environment, and policy making. We make policies, or the policymakers make policies, but they have to have some rationale for their policies, right? That the impact, the policy goals, can they achieve their policy goals? What are the costs for them to achieve those policy goals? Are there unintended consequences? Who will be impacted, and by how big? And those are the questions to provide the evidence to persuade the ratepayers, the voters to support such policy, right? So through EST 603, I hope you will be equipped with those kind of skill sets. For sure, we will give you big picture of different energy systems, and models to analyze those systems. Some field, for example, power systems, are way more complicated than this class can offer you. So we may, if you want to have deep dive, you may need to go into the depths that you may need to take another class, or try to find more materials that can help you develop the depths needed for a specific question or specific system. But for this class, I hope to expose those systems to you or those tools to you. Organization, please review the syllabus, which is both available on Brightspace and the online course website. I'll talk about the course website a little bit more. As I mentioned, Brightspace will be our main online platform. All class material assignments will be posted on Brightspace. I'll try to organize more modules by each week, so you know where to find them. So all materials, weekly materials will be in one module. So it's very easy for you to follow, including the lecture slides, the recording, and if there's any assignment, you can also find there. Course website. Course website is mainly for the access for your devices, because I already prepared the material anyway, so I just posted there. If you check on your phone or your iPad, you may find this website easier to look at, but you don't have to go to the website, this website, to the material. All material will be posted on Brightspace. Homework. I hope if you have sourced the design of the homework, we will have 4 measure homework, each 10 points. So this is very important. I try to get some feedback from you. If you have, do you want more homework, and each has less share of your total points, or you're fine with full homework? And homework, I will post at least 1 week before the due date, so you have time to work on it. Very often those homework ask you to use quantitative analysis or models to answer some policy questions or real world questions. Proposal, that's your final project. As you can see from here, final project is about 60% of your grades. So very important. So by middle term, you would plan to submit a proposal, 1-page proposal, to tell me what you plan to do for your final project, and what models, what data you have to develop your final project, and I'll provide some comments for your project. So put some thoughts on it. This project, I'll post some examples from previous years, and you can also think about some real-world questions or investment decisions or policy decisions, and try to use models to evaluate their impact, their costs, etc. And then you are asked to do a final presentation, which is about is 20% of your final grades, and policy memo or policy paper, that's your final paper, which is 30% of your grades. So that's roughly the organization part. So the contents of our class, so it's an energy system analysis, right? So we will talk about the energy systems, and we will talk about the analysis. For the systems, we will talk about data, which is key for the analysis. Yeah, that's like the food for the model, and the project economics, the fundamentals that will make sure we get the economics right when do analysis. Different technologies, solar, wind, conventional technologies, hydro. So those understanding fundamentals of the technologies will help us to understand the analysis needed from supply side, and from those technologies. We will have less coverage on the demand side technologies, but those are very important. You may need from the other material to have more in-depth discussion. Demand, we will talk about the drivers of a demand, but not necessarily specific technologies. For example, energy efficiency. There are so many devices, so many appliances. If we talk each of them, then we wouldn't have time to cover other material. Power system, as I mentioned, is very important because the overarching design of our energy system, let's say we have a grand challenge of a climate change, right? In order to address climate challenge, we have to decarbonize our energy system. But how to decarbonize? So the overarching design is, first, we electrify our energy use. Why? Because electricity is a high quality energy service. And with electricity, we change our energy use or energy production from more distributed to more easier control style. The electricity can come from renewables, not necessarily coal plants or gas plants or oil plants. So that makes the source, makes the decarbonization part easier. So two fundamental ideas, right? First, electrify our energy use. Second, try to decarbonize our electricity source. So that's energy system. And in addition to energy system, because energy is embedded into our economic systems, and energy systems also has environmental impacts. So we will also cover energy, environment, and economy. That's the triangle we will discuss more later. Tools, skills, I would say data analysis, because increasingly energy data are big data. Think about meters, think about when we deal with solar, wind, those are variable resources. They change with the climate, with the weather data. So you would have hourly, even sub-hourly data to do those analysis. Economic analysis, our energy demand, our electric load change very fast, and some of the data also available. I hope you will get familiar with the data and analysis. For environment, we will talk about life cycle analysis, which are fundamental for us to think about how to choose, compare different technologies, in addition to the economic analysis, like levelized cost of electricity, levelized cost of energy. What's the investment cost? And we will also discuss some concepts like learning curve. how we make assumptions of the cost of the future technologies, and learning rate will help us to make the right or acceptable assumptions. Again, some analysis will rely on the system thinking, like energy, economy, and the environment, the so-called Lexus analysis, because increasingly our energy system is constrained by water. If you pay attention to recent news, there heat all around the world, and many energy systems has facing water constraints. For example, hydro plants in southwest China lose the capacity because the plants do not have enough water to generate hydro power. And even for coal power, they need water for cooling. And with heat, the power plants lose partial of its efficiency, and it requires more water for cooling. So those are why the systems are integrated, and we have to think about as an integrative analysis. So we will talk more when we reach specific lectures, but overall, you can think of energy systems and related economic and environmental analysis, and then the right tools and skills to analyze those complicated interactions, trade-offs, and system involvement. We are talking about energy system analysis or energy modeling. I'd like to start with two quotes. I really like them. The first one, you probably hear a lot. It's from George Box. And what his insights on modeling is all models are wrong, but some are useful. So what does it mean? First, models rely on data and assumptions, and also rely on our understanding of the structure, the system structure. And all this can be flawed. Data not perfect, not complete, and sometimes can wrong. And assumptions may change. Our cost assumptions can change very quickly. And our understanding of the structure might be wrong. So in that sense, all models are wrong because inputs already wrong, and how can you get the right model, right? But some are useful, which means we are not trying to build a perfect, accurate, correct model. We are using the model to simulate, to rebuild the real world, and to try to understand the relationship between different moving parts. And those understanding can be very useful for our analysis, to support our decisions. That's why it's called all models are wrong, but some are useful. So we are not trying to build a perfect model. We are trying to build a useful model. Second one is from Albert Einstein, that it's kind of philosophical. It's not really tell us how to do it, but philosophically, it shows what our goal is. Everything should be made as simple as possible, but not simpler. How to really understand this quote? Okay. Our systems, energy system, economic system, environment system, are all very complicated. And the scale can be at very different scale. We talk about hundreds of scale, hundreds of years, decades, days. seconds, different scale, very different research questions that we need to address. For example, when we talk about renewables, those change regularly. Very fast, right? Wind come and go. Some, if the clouds come, solar radiation can change. So if you try to understand the impact of the renewables, probably you need a higher resolution, temporal and geographic resolution model to really understand the impact. But if you work on nuclear, for example, it can run high reliability most of the hours in a year. So you probably don't need a high resolution model to do it. So depends what's your question, what's your variables, what's your technology you're talking about. You may need a different compilation of data and thinking of the model to answer the question. So that means you need a sophisticated enough model to address your question, but at the same time, you don't want to trapped in your data collection, in your model validation, because the more nuance you have, the more variables you have, the higher resolution you have. Those all make the model complicated, and you have more risks that you may end up, the model might end up not working well. So philosophically, this tells us we want to as simple as possible, but not simply as we don't want to lose the detail that is necessary to address our question. So what is energy system analysis? As I mentioned, we also call it energy modeling. We very often use computing models to simulate, to design, and operate energy systems. Some questions we can answer, for example, what are our energy needs? What's the demand for the next day? You may think about the temperature, if there's rain, if there's a big event. There are many moving pieces that human behavior, driving, or where we are using those energy. And then the utility company or the energy supply company, they can plan for their generation, for example, or delivery. So it's key for them, right? Investment, they can think about where they can put their investment. Even stock trading, they can see where they can make money or have upcharge power, right? What infrastructure do they require? Energy heavily rely on infrastructure. Power grid is a huge infrastructure. Oil, gas pipelines, right? Those are all without infrastructure. We cannot enjoy the service. So where should we build? Where should we build the infrastructure? Where should we build the power plants? Where should we find the linkages? What are the environmental climate impacts? Especially now, this US administration, the Biden administration, focus a lot on justice, right? Who are impacted? Are they underserved community? Are they disadvantaged community? Because let's say EV is great, right? But EV, you wouldn't need more power to charge the EV. And if the power plant are coal power plants and they locate nearby the disadvantaged community, then EV you end up polluting more to the disadvantaged community. So that's a project that I'm working on. So it's an example, right? And how much will it cost? In the end, those will impact, should we do it and when we can do it. You will see questions or designs like social cost of carbon, social cost of or the true cost of energy, which include those environmental and social impacts. Why models? We can answer some questions without a model. Some may intuitive, some may back of the envelope calculation, and why in the first place we need models. Models help us to think. So in order to build a model, you would need to understand the system, the relationship, the structure, and those things help us to think. So with the model, you can do projections, predictions. In the engineering world, you probably need more prediction, more accurate. In the policy field, probably we use more projection, which means that if this happened, what would happen? It's not say if this happened for sure, something will happen. So models can help us to simulation. Models can help us to find the optimal mix of energy system, for example, optimal investment mix, and optimal operation schedule, for example. That bring a lot of level of control problem when you start to generate renewable. When you have renewables, you would reduce your generation from fossil plants, for example, but this need to control, especially renewables are increasingly distributed, and there are many on and off control problems in the energy system. No need to say the system evolve. So in some cases, we need stochastic and dynamic modeling. And in the policy discussions, we need scenarios that can help us understand different policy scenarios. Just a quick example. What if we want to achieve net zero emissions by 2050? What if we want to achieve more than that or less than that? What's the implications? So we can discuss, design different policy scenarios for those needs. Modeling is very hard, and even the top institutions not necessarily get models right. Here are two examples. One is from EIA, which is Energy Information Administration of the United States. It's part of the DOE, but more is a bipartisan, independent, as they declared. Each year they have their annual energy outlook. This is each year they put out their projection of future coal consumption, right? And as you can see here, the actual coal consumption for electric power is decreasing due to the fact of competition from gas plants and the development of renewables. So each time they underestimate or they overproject the coal consumption. Another example is from IEA. These two institutions very easy to mix or can be confusing. Please try to differentiate. I hope if you cannot differentiate these two institutions, you're not in my class. IEA is International Energy Agency. EIA is Energy Information Administration. Okay, I hope you get the names right. So IEA can be because it's the OECD institution, and it has the world best modelers, and each year they have a flagship report, the World Energy Outlook, and here each line represents their projection of the future expansion of solar PV and additional solar PV in their World Energy Outlook, as you can see here. And the bold black line shows the real what's the historic additional solar PV each year. And this is their model always underestimated. So even the world famous best modern team could get things not so wrong, but missing the measure trend of renewable development and coal phasing out. Why? I'm curious, right? There are many reasons, different reasons, but I categorize it as risks and uncertainties. Risk is, as I mentioned, models rely on data and assumptions, right? Data and assumptions drive results, but those data and assumptions based on historic experiences, and that's usually is okay because in a stable system, history predict or project the future, but it could change, especially some structural change. One example is the shale gas revolution. In the 2010s-ish, 2010 to 2015 area, shale gas becomes just increasingly cheaper due to the fact of technology revolution. It's called horizontal drilling because we use for oil, we use vertical drilling, right, to drill into the depths that we can reach the oil deposit and we get the oil out. But shale gas deposits in the deep shale formation of the geologic layer. It's very hard because it's spread. The horizontal drilling is you can first drill down to the geologic layer, and then you can go horizontally, so you can reach way larger area to extract the gas, to let the gas flow to back to the surface. And another is fracking, hydraulic fracking. So once you reach the vent, you need a high pressure to break the rocks so the gas can leak out, right? So those technology breakthrough help bring down the cost of the shale gas extraction, and shale gas becomes available. That's what you see. Part of the reason of the coal phasing out, competition for renewables and shale gas. Uncertainties. We know some technology would change, right? For example, if we talk about fusion, and that can be a game changer. For example, we are talking about renewables, we are talking more about that. And renewable costs are really getting cheap. But 10 years ago, we didn't expect that. Let's say 10 years ago, the prediction is we might achieve grid parity, which means renewables can compete with the conventional electricity by 2050. And 5 years ago, the projection is by 2030. And now renewables are already competitive. So the exact timing and the characteristics of the pivotal events or technology change is unpredictable. When fusion will become economic variable, we know someday it might, but we don't know when. 30 years, 50 years, we always say in 50 years it will be economic variable, and we are still say 50 years, right? So these two main reasons, for example, for sure there are many other different reasons, but these two emphasize the difficulties. Energy systems are complicated. Here is a chart from EIA that it has all the infrastructures of US energy systems, power grid, pipelines, stations, power generation stations, and some power plants they can use dual fuel, which means they can use gas, they can use oil. No need to say increasingly more renewables. It's a massive, gigantic systems. It's such a massive modern infrastructure and so complicated that any segment or any changes in the system can impact the whole system, and no need to say increase the impact by climate change. As I mentioned, heating, extreme weather or floods, such like that, or sea level rising. Another complexity is from the energy so-called trilemma. Really balance the trade-offs between energy security, energy equity, and environmental sustainability. Some people call it the impossible trilemma, that you, as a society, we have multiple goals, right? And for energy, we want it to have reliable energy supply. We want it to be affordable for poor or disadvantaged communities, and we want it to reduce the impact to our environment and the climate. And in the end, we found it might be impossible to achieve all those goals because some goals there are conflict. If we want more climate friendly, we would use more renewables, but renewables are variable, so they may not be reliable, right? Now it's getting cheaper, so it's more affordable now. And for nuclear, for example, it's reliable service, but it has potential impact to the local community. So for energy decision, really needs to balance the different goals, and sometimes we would find a very hard trade-offs. Also because we are talking about energy in the context of energy economy and environment. For example, economic development will impact our energy demand. There are discussions of is continuous GDP growth our goal, or we just pursue some so-called decent living. And what is decent? And school of experts also even discuss maybe we should degrowth to reduce our energy need. And all this will impact the fundamental assumptions of our energy analysis. How much electricity, how much energy you need by a future year or something like that. And that would impact the infrastructure, the investment, the system we want to prepare from today, right? And environment is very important, especially if we see climate change as part of the environmental change. We need to think about the climate goals to have net zero emission by 2050, so we can control our temperature change not more than 2 degrees C, or even we can achieve no more than 1.5 degrees C. And ecosystem constraints, land use, energy projects take lands, right? And where we build them and what's the impact to ecosystem. For energy, we have to work within those constraints. And that's getting complicated. Okay, but we had achieved great achievements. These from national academies, the greatest engineering achievements of the 20th century. The first one is energy, right? The electrification for human society. Now we know there's still billion population may not have access to electricity or have reliable service of electricity, but human society as a whole has enjoyed the modern life enabled by electrification. Just think about it, without electricity, education, communication, health service, all the fundamental human service would not be possible. And we would understand how much we have achieved in the history. And still far away to go. Want to have clean energy for all by 2030, and to achieve climate goals, and these UN Sustainable Development Goals. Energy is a big component of it, and we still have a long way to go. If we talk about 2030, it's only 8 years away, right? And it's very, very pressing challenge for the world, and grand challenge to address climate problem. We have to decarbonize our energy system, because carbon emission, for sure, some come from land use change and then the cover change, but the big problem, 3/4 of the problems come from the energy system, and we have to decarbonize our energy system in a rate that unprecedented in history. By 2050, even before 2050, we have to achieve net zero energy system. This would require fundamental change of how we generate electricity, how we use our energy, how we transform our transport system, industry, international travel, all those energy consuming sectors that would need to revolution. You can say that the energy revolution, from supply to demand to the transformation sector. And modeling can be useful and insightful. I may offer a quick example, but modeling can build the structure, help us to understand how systems work, and it can demonstrate the relationship between the moving pieces, assumptions, and the results. And with some visualization, it can help us to visualize the changes, the relationship, and the results, and to visualize the communicating messages. And it will inform the lawmakers, decision makers, public, the impacts. So we can take those impacts into our decisions. One example is renewables are achieving grid parity, and we see this as a structural change. This chart from International Renewable Energy Agency that from 2010 to 2021, solar PV, for example, the cost has decreased more than 80%. Onshore wind, very similar story, and the cost of renewables really getting cheaper and achieving grid parity. So this is a structure change, and it's a game changer. And the implications, one paper from Grant, one paper is my own paper. We studied the impact if we integrate the cost change and predict the future, assume it will continue in the future, and it will accelerate or enable the renewable expansion in the energy system. I focus on the power system and use China example. So it will add 10% more share of renewables by 2030 compared to the conventional projections if we take into account of the cost changes. And that's and what's more is a renewable dominated power system would be cheaper than the conventional or the business as usual scenario. That means moving to a renewable dominated power system is not just technologically viable, but also cost effective. And that change our perception of or thinking of renewables, because people may argue renewables are more expensive. Renewables are not there yet, and the implications are profound. Another implication, you may heard about carbon capture and sequestration, CCS. The idea of a CCS is we can inject or suck carbon emissions from atmosphere or capture carbon from power plants, then storage it to the geographic layers and permanent storage. So we keep the carbon underground. It used to be saying without CCS we cannot achieve it, but now we have cheap renewables, and that cheap reduce our reliance on such geoengineering to deal with the carbon challenge. It doesn't mean we don't need a CCS anymore, but the value of a CCS has significantly reduced by cheap renewables. You can, if you are interested, you can use the link to get to the paper. So that's example. So let me end with two quotes. I started with two quotes, like George Box and Albert Einstein. These two quotes help us to how do we interpret, how do we understand models. One from Bill Hogan. Let's see it is not the individual results of a model that are so important. It is the improved user appreciation of the policy problem that is the greatest contribution of modeling. You can see modeling as a consensus building. When you build a model, you engage with policymakers, with stakeholders to get their insights, their perception, and you try to integrate those insights in your model, and you come up with some results, and you get feedback from the stakeholders, and the process itself is modeling, right? So modeling helps to build such consensus among stakeholders. And when everybody makes sense of the model, then your model already make a contribution. Second one is the primary goal. This is from Huntington Weald. Those are professors at Stanford Energy Modeling Forum. And from their report, modeling for insights, not numbers. So as you can see here, the primary goal of policy modeling should be the insights quantitative models can provide, not the precise looking projections, for example, numbers. That means, let's say I just give an example of my paper, right? I mentioned it can achieve more than 60% of the power system can get from non-fossil electricity. This includes nuclear. 60 itself might not important, or 62 in our results. It can be 65 or 60 or just 60. The number itself may not that important as the insights, which is with cheap renewables, the power system can be less carbon and cheaper. That's the key insights, right? It's not just technologically viable, but also cost effective. That message is more important than how much electricity can come from renewables. So I hope this idea is communicated. So all in all, models can help us framework to help think, to build consensus. At the same time, we need to be very careful to interpret the results. And those are some references that cited in the presentation, and you can always check the full paper if you are interested. Okay, let me stop here for the introduction, and I'll post the lecture on Brightspace.